All right, guys, so in 8.4, we're going to talk about this thing called conditional probability, which is a concept that we've discussed in the past, but we're going to formalize it and calculate a few different things and interpret those results now. What we're going to start off with is some new terminology, and that would be when you see something that looks like this. All right, so what this means is the probability that A is going to occur given that event B has occurred. And so this changes the way we set things up a lot of the time, because if I just ask what's the probability of A, that could be one thing. But if I want to know the probability of A given that B has occurred, that changes our numbers sometimes. So we're going to see how that affects our probabilities that we're going to calculate with this table of information about transportation methods in New York, LA, and Chicago. So we're going to analyze this table over here. 3 major cities, 3 major ways to get around, and we're looking at how often people choose to use these modes of transportation in each of these cities. So for example, people take the train in LA about 0.12 or 12% of the time. Civil engineers are trying to make determinations about how to support public transportation. So what they want to know is a person more likely to prefer cars if they live in New York or if they live in Los Angeles? So what we want to know is the probability of preferring cars given that a person lives in New York the same as the probability of a person preferring cars given that they live in LA? So we want to find out which of these is greater, or maybe they're equal, but we'll make a determination about our results from these two probabilities. So how do we figure these out? Well, let's first focus on the probability of a person taking a car or preferring a car if they live in New York. Let's figure out how this is going to change our probability, because if I just say, what's the probability that someone takes a car? That is 0.31, right? 0.31 out of 1, out of the total amount. So 31% that someone prefers a car. But this changes if it's given that the people are from New York. So what that kind of means, I'm just going to use a highlighter here just to black out all the stuff that doesn't matter. It doesn't matter any of these numbers about LA or Chicago because it's given that we're in New York. So since that is given, we're going to focus only on the people who live in New York. And of those people who live in New York, how many of them prefer a car? So since we're starting with just the people who live in New York, because those are the only people we care about, when we calculate this probability, that's our number of possible outcomes. In this case, 0.40, because 0.40 of the population lives in New York, right? That's our total. That's how many people are in New York in this survey. And of the people in New York who are in this survey, how many of them also prefer to take the car? And that turns out to be 0.05. Which we can reduce this fraction and get 1/8. All right, so that's a number that might help us. But let's do the same thing for the probability of someone taking a car given that they live in LA. So if I'm going to calculate the probability that someone takes a car given that they are in LA, I don't care about any of these other groups. I'll use blue this time to cross out the stuff we don't care about. Don't care about New York people. Don't care about Chicago people. I only want to know what's going on in LA. So these are the people I'm focused on right now. So of the people who live in LA, of which there are 0.35 out of the whole survey, how many of them prefer cars? 0.18. Because I'm only asking how many of the LA people prefer cars. So I could try to reduce this, but really all that I'm going to do is just remove the decimal places or decimal points. So I have 18 out of 35. And this is a case where it's hard to compare these. I'm going to have a tough time getting a common denominator between 8 and 35. And so what I might do with a calculator is just divide these. 1/8 is approximately 13%, and 18/35 is approximately 51%. And so our question is a person more likely to prefer cars if they live in New York or if they live in LA? And based on these numbers, I would say that a person is more likely to prefer cars if they live in LA, because there's a 51% chance of that, whereas the probability that someone prefer cars if they live in New York is approximately 13%. So this is where I would make my therefore statement, and I've proven that therefore people who live in LA are more likely to prefer cars than people in New York, and that's just based on the comparison of those two conditional probabilities. Let's do one more example of these. So here we're asked to draw a Venn diagram below to represent the people in this classroom who S have at least one older sibling and who D have driven a car before. So in this case, we would want to fill this Venn diagram with possible information about you guys in the class. And unfortunately, we're not in person, so we can't actually do this in person. I'm going to make up some results based on last year, the results I had in class when I taught this lesson. So we're going to have a Venn diagram here. It's another way for us to organize data. And we have all of the people in the classroom. So all the people in the room, that's not defined to be a variable, but we do have S, which is the people who have at least one older sibling, and D, the people who have driven a car before. So last year when I did this, and again, this might not be the same this year, but these were the numbers we had. 3 people had at least one older sibling and had driven a car before. 7 people had at least one older sibling but had not driven a car before. 4 people had driven a car before but didn't have any older siblings, and 6 people had neither of those. So with these results, we could calculate some conditional probabilities, like D, given something else. So first, let's take a look at the probability of D and make a general statement about the likelihood of this event. What is the probability of selecting a student at random from this survey who has driven a car before? And so this is just your basic, how many people are in the survey, and of those people, how many have driven a car before? Well, the number of people in the survey is 20. If you add up all of these numbers, you get 20. And of the people in the survey who have driven a car, there are 7, right? That's all these people. They've all driven cars before. So you could say that there's a 7 out of 20 chance, or there's a 35% chance of randomly selecting a person from this room who's driven a car before. Now, how does this change if we ask this question instead? What's the probability that someone has driven a car before given that they have an older sibling? This changes because now we only care about people who have had older siblings, and so we kind of can gray out the group of people who don't have older siblings. These people don't count. They don't have older siblings. These people don't count. They don't have older siblings. So what we're asking is, of the people who have older siblings, how many of them have driven a car before? So when I calculate that probability, I only care about how many people have at least one older sibling. And it looks like from this data, 10 people have at least one older sibling, right? These are the groups that are left. 7 plus 3, 10 people have at least one older sibling. And of those people, 3 of them have driven a car before. So I would say there is a 30% chance of selecting someone from this room who has driven a car before, given that they have an older sibling. So the way that we keep calculating these probabilities, it might be useful for us to kind of tighten it up and put it into a probability formula. But anytime I do this, so in this case, when I calculated the probability of D given S, I keep following the same pattern, right? Our denominator is just the number of possible outcomes, which has been changed to be the set of all things S. Or in the example above, in this example, it was the set of all things New York. This example was the set of all things Los Angeles. So the denominator changes a little bit to include only the probability of that second event. So if it's given in this case that they have older siblings, when we calculate that probability, our denominator is going to be the probability that someone has siblings just in general. And then our numerator is going to be the probability of driving intersection siblings. And this is a formula that we'll keep using. So just generally, if I want to find the probability of A given B of 2 events taking place, then in this case, since B is given, I only care about, of the elements of B, how many of those elements are also in A. And this formula is the formula that we will use to calculate all conditional probabilities for the rest of this unit, and it's something that we'll do pretty regularly. So tomorrow's lesson is going to be the practice based on this. Make sure you've watched this video and answered the question, and if you have, then you're good for today.